In the preceding activity, you showed how to generate values for random variables from a generic discrete distribution, a uniform distribution, and a normal distribution. Generating values for a normally distributed random variable required the use of norm.inv, that is, to return the inverse of the normal cumulative distribution, and the rand function. When using the Excel formula, it will generate a random variable r between 0 and 1, and then the norm.inv function identifies the smallest value of k such that p sub x is less than or equal to k, such that k and x is greater than or equal to r, where x is a normal random variable with mean and standard deviation. Similarly, the rand function or the random function can be used with Excel functions beta.inv, binom.inv, and gamma.inv, and as well as the lognorm.inv to generate values for a random variable with a beta distribution, binomial distribution, gamma distribution, or log normal distribution. Using a different probability distribution for a random variable simply changes the relative likelihood of the random variable realizing certain values. So the choice of probability distribution to use for a random variable should be based on historical data and as well as the knowledge of the analyst. We can reduce the width of the confidence intervals associated with the sample mean and the sample proportion computed from a sample mean or from a set of simulation trials by increasing the number of trials beyond 1,000. So in your activity, you have the trials of 1,000. However, increasing the number of trials can begin to tax the computational capabilities of Excel. When more than 1,000 trials, it is necessary to reduce the sampling error. For this time, the analyst may want to restrict Excel to only update values upon a specific command rather than updating any time the Enter key is pressed in Excel. So this can be accomplished by choosing File menu from the ribbon, clicking Options, and choosing Formulas, and then changing the calculation options to manual. When this change is made, Excel will update values only when the F9 key is pressed. So now let us have the simulation considerations. How will you verify or know that your simulation is correct? An important aspect of any simulation study involves confirming that the simulation model accurately describes the real system. In some cases, that inaccurate simulation models cannot be expected to provide worthwhile information. Thus, before using simulation results to draw conclusions about a real system, one must take steps to verify and validate the simulation model. So we have verification and validation. And in this topic, we have also the advantages and disadvantages of using simulation. So for considering simulation, we have to verify and validate. So what is verification? So it is the process of determining that the computer procedure that performs the simulation calculations is logically correct. Verification is largely a debugging task to make sure that there are no errors in the computer procedure that implements the simulation. In some cases, an analyst may compare computer results for a limited number of events with independent hand calculations. In other cases, tests may be performed to clarify that the random variables are being generated correctly and that the output from the simulation model seems reasonable. So the verification step is not complete until the user develops a high degree of confidence that the computer procedure is error-free. So now we have the validation. So this is a process of ensuring that the simulation model provides an accurate representation of a real system. This requires an agreement among analysts and managers that the logic and the assumptions used in the design of the simulation model accurately reflect how the real system operates. And the first phase of validation process is done prior to or in conjunction with the development of the computer procedure for the simulation process. So validation continues after the computer program has been developed, with the analyst reviewing the simulation output to see whether the simulation results closely approximate the performance of the real system. If possible, the output of the simulation model is compared to the output of an existing real system to make sure that the simulation output closely approximates the performance of the real system. If this form of validation is not possible, an analyst can experiment with the simulation model and have one or more individuals experienced with the operation of the real system. So the simulation output would determine whether it is a reasonable approximation of what would be obtained with the real system under similar conditions. So the two, verification and validation, are not tasks to be taken lightly. They are key steps in any simulation study and are necessary to ensure that decisions and conclusions based on the simulation results are appropriate for the real system. So, what are the advantages of using simulation and also their disadvantages? The primary advantages of simulation are that it is conceptually easy to understand and that the methods can be used to model and learn about the behavior of complex systems that would be difficult, if not possible, to deal with it analytically. Simulation models are flexible, as it said. They can be used to describe systems without requiring the assumptions that are often required by other mathematical models. So in general, the larger the number of random variables a system has, the more likely it is that a simulation model will provide the best approach for studying the system. So another advantage is that simulation model provides a convenient experimental laboratory for the real system. I repeat, it provides a convenient experimental laboratory for the real system. Changing assumptions or operating policies in the simulation model and rerunning it can provide results that help predict how such changes will affect the operation of the real system. Experimenting directly with a real system is often not feasible. Okay, so it needs experimental rerunning if possible. Simulation models frequently warn against poor decision strategies by projecting disastrous, as it said, outcomes such as system failures, large financial losses, and so on. Yes. So it takes a long process. Simulation is not, or it, there's no such thing that without disadvantages. So simulation is not without disadvantages. So for complex systems, the process of developing, verifying, and validating simulation model can be time consuming. Yes. So it takes time to experiment the laboratory for a real system. Mm, can be time consuming and expensive. Yes. However, the process of developing the model generally leads to a better understanding of the system, which is an important benefit. Like all mathematical models, the analyst must be conscious of the assumptions of the model in order to understand its limitations. In addition, each simulation run provides only a sample of output data. So, as such, the summary of the simulation data provides only estimates or approximation. That is why, while rerunning your data, there are different value. There is no proximate value that came out upon running the data. Nonetheless, the danger of obtaining poor solutions is greatly mitigated if the analyst exercises good judgment in developing the simulation model and follows proper verification and validation steps. So, furthermore, it is sufficiently large enough set of simulation trials is run under a wide variety of conditions. So the analyst will likely have the sufficient data to predict how the real system will operate. Okay, so that's the end of the Monte Carlo simulation, which is the simulation is a method for learning about a real system by experimenting with a model that represents the system. And what are some of the reasons that simulation is frequently used? It can be used for a wide variety of practical problems. Another one, another reason is the simulation approach is relatively easy to explain and understand. And so, as a result, management confidence is increased and the results are more easily accepted. Lastly, spreadsheet software such as Excel and specialized software packages have made it easier to develop and implement simulation models for complex problems. So, in this chapter, as a summary, we showed how the native Excel functions can be used to execute simulation models on several examples. Like in your activity for the Sanotronics problem, we used simulation to evaluate the risk involving the development of a new product. Then we developed a simulation model to help the other company to estimate how varying its bid amount affects the likelihood of winning a property auction. Okay. So following the steps for conducting a simulation analysis, like we have focused the Monte Carlo simulation. So the first step is construct a spreadsheet model that computes output measures for given values of inputs. After this step, identify the inputs that are uncertain and specify a probability distribution for these cells rather than just static numbers. Third step is select one or more outputs to record over the simulation trials. The fourth step is execute the simulation for a specified number of trials. Because as it said, to validate, so it needs rerunning your data. And the last step is analyze the outputs and interpret the implications on the decision-making process. Okay, that's the end.